So the next one is the format string vulnerability, which is pretty amazing. All right, you might realize that all the problems are caused by C. All the problems we've exploited so far are caused by the way C handles the things it calls strings. Strings are just null-terminated byte arrays, and it isn't intelligent enough to notice if you put in something too big, which is pretty ridiculous. All modern languages like Python and Java would not let you do this. If you try to put in something longer, it will just allocate more memory. But C doesn't, and that's the problem. And here's an even crazier thing about C. These format string vulnerabilities happen because when you do let me bring up this program, ED204. We get out of here and go to 127, ED204. Okay, so here's my program. All right, so what we're doing here is, all right, okay, when you print something in C, what you're supposed to do is you're supposed to print it like this. You have a thing called a format string, and then the variable you're printing. So this is the structure, and you have somewhere you have a control character like %s, which means a string goes there, and you put your string here. But you can do this. Now this is a really bad idea. I don't know why they let you do it, because it's horrible. But we're going to see several reasons why C is insane. I can print something without specifying the format string. Well, then it will just use a default format string and print it out. That's fine, but if you look at the assembly code and see how these things work, you'll understand why this happens. This is a terrible thing about the way, when you call a program with arguments, it is several machine code instructions are used to do this. What it does is it pushes a pointer to this argument on the stack, then it pushes a pointer to this argument on the stack, then it calls the function starts, it doesn't know anything about the calling program, so it runs and it looks on the stack to find the arguments. Whatever it finds there, it believes it's the arguments. So when this thing runs this print, it doesn't know whether you had a format string or not. It just looks at the first thing, and if it looks like a format string, it says, oh, there must be another one after it. So this means you can do insane things. If I run this, ED204, and I want to print a string. Okay, if I print the string hello, it's fine, it prints hello. But if I put %x here, then it's a format string. And so it prints some number in hexadecimal. The first thing it found was now a format string, so it takes whatever the next thing on the stack is and prints it, even though I was not intended to see that. So this is an information disclosure vulnerability. I'm seeing raw memory. This, by the way, was what Heartbleed was. Heartbleed just let you see raw memory, and that turned out to be terribly important, because you would find stuff in there like other people's passwords, the private key for the for the server, and all sorts of good stuff. And you can have as many of this as you want, %x, %x, %x. You can have a whole bunch of it, and you can put in printable characters just like you could in any other format string. So you can have delimiters. Okay, so that's pretty bad, but here's what's even worse. For some ungodly reason, there's a format called %n. And what %n does is it takes the binary value it finds, treats that as an address, and writes to that address. Instead of reading, it's writing from the print command. So if I put in %n, then weird things happen. I put in a few of these, it's going to crash the machine. It's taking whatever numbers it found on the stack and writing to those locations in memory. I have no idea what the purpose of this was. I assume it must have been for formatting something, but this is incredible. So now here's another fun fact. How do I control what's on the stack? Well, the stuff I put right here goes on the stack. So if I run this, and let me go back here and make sure I got my, to control a parameter, yep, there we are. I just put in some characters here like A, and then $%x. So here's the A's I put on the stack, and there they are. The data I put at the start of this goes on the stack, and if I print the stack, after a while I'll find it, so I can insert anything I want on the stack, and then I can write to that memory by putting in a %n. So I now have an arbitrary write where I control the address. The only thing I don't control is the value that's written there. which it turns out the value that's written there is equal to the total number of characters that have been printed so far. That's why apparently the purpose of this was to format some structure of a line you were going to print, and apparently nobody thought of the mind-numbing security consequences of designing language this way. So if anybody does a print statement and they forget to put the format string in it somewhere in your code, you can do this nonsense. It turns into an arbitrary write. So there's only a few more tricks. The next thing is, how do I take over the box with a write operation? Yeah. 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 What's that? The binary, I'm sorry, I didn't understand. The binary is what? It is 32-bit, but it's the same. Yeah, it's through file. Oh, yeah, good. Yeah, I think I made it 32-bit. That's why we're seeing 32-bit code, yeah. If it was 64, I think it would do 64-bit. Yeah, good question. I don't think I've tried a format string in 64-bit, but I think all that would happen is you get 64 bits instead of 32 bits at a time.
How do you know it's 32-bit?
Oh, it tells you right here, F32-bit executable. That file command is good for that. Yeah, and this is yeah, it works on ARM too, of course, but I'm doing the 386 version now. Yeah, good. Anyway, so in order to take over the box, you need to find some place where you can write and control the instruction pointer. And it turns out there are a lot of good, now you could in principle write to the end of a buffer, but that would be a little tricky because those buffers are temporary. What's better is to go to the relocation records. Now, if you think about what happens, you have compiled code on, say, a Windows machine, like Notepad or something, then you might update the operating system. When you do, the address of the Windows API calls will change. And you don't want to have to reinstall your code, so you never jump directly to an API call. You jump to a pointer which points to the function. And when you run a Windows update, it updates the functions and it updates the table pointing to the functions. So you find the right function. And another thing you might do is you might update your software and compile it with a later version of the compiler, which would change the structure, and you still want to reach there. So there's two steps of relocation. You jump to a relocation record associated with the program, and then another one going through the operating system, and that's what you're seeing here. So this is, if you run the, you can see it here. And it's what are called the procedure linkage table and the global offset table are these two tables. And the obj dump program will show it to you. So the obj dump program, which included in Linux, will show you the library functions used by this program and their relocation records. So when you go to exit, for example, this is a real simple program. All it used is print, string, copy, and exit. And so print is here, stir copy is there, exit is there, and you can see they're all very much the same because this is just a list of pointers. This is not the actual address of the C libraries, it's the pointers to the system libraries. But the point is, if I write a different address to this location, then when the program tries to exit, it will go there instead. So this is a place where if I write there, the execution will use that address. So that's how you gain control of the EIP with a write operation. There are other places, but this is one handy place. It also means, by the way, I can't use the exit function anymore. So you have to find a function that is used only after your exploit, or you'll break the code. Like if I broke print, it wouldn't even be able to get to inputting the data. So that's the point. So now I can write to it. So if you go in the debugger and you examine that pointer, it'll have the actual address leading to it, which is a 0804 thing. If you then run this thing with the %x, 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 %n, it will write to that location, and now it's going to contain the value 1b, the small value, which is just the number of characters printed so far, which is about 30. So, and now, when the program crashes, it's going to, if the program stops, it's going to crash because they can't exit properly anymore. It's going to go to an invalid address. So now you have to put in a valid address. Now, the problem is, you want to put in like 0804 something to point to some code, but that's like around 2 billion. So you'd have to write 2 billion characters, which is insane. So you don't do that. What you do is you write a number of characters only going up to 256, and you only care about the least significant byte. Then you make another write 1 byte beyond it, and you write the bytes one by one. So here's the structure you make. You want to write to each one of these 4 addresses in turn, and so as you do that, you're going to write each them one by one, and you will create this kind of address, 30, 38, 40, 48, because each one of them prints 8 more characters. So you can write all 4 bytes one after the other, and by the way, each one of these is a 32-bit write. So you write 30 and then 3 bytes to the left, and then this one and 3 bytes to the left, so you get the bytes you want, and you do 3 bytes of collateral damage to higher order bytes. You're destroying some other pointer that you hopefully don't care about. A lot of exploits have collateral damage. This is why a lot of attacks crash the server or do other harm, especially if you write them sloppily. But anyway, now I'm controlling. So now if I want to target a specific value, I'm going to have to increase it, and I'm going to have to use multiples of 256. So that I'm controlling the last byte. So the first byte is 256 plus something, the next byte is 2 256s plus something, 3 256s plus something. That's how you can get there, and you only have to write a few hundred or 1,000 characters to reach all the values you need. That's why I say it's a little tedious, but I can hit this value, AA, BB, CC, DD, by having this, and what happens is there's an offset, which is this 29, and you just have to adjust it experimentally to make it work. Which is how many characters are printed before you started this. So you can gradually build the address you want. And if you look in here, you'll see AA, BB, CC, DD. So now I can hit any address I want. So now I do the same thing we did before. I have to make a NOP sled and shellcode. And I make the NOP sled 90 is NOP and CC is break that returns to the debugger. So if you want to just make a prototype exploit to find out where the addresses are, you can just put in a NOP sled and a shellcode. I put in 100 NOPs and 250 shell breaks just so I can practice. Then you can run it, look at it in the debugger, and you can find your NOP sled. Here's my NOP sled with 90s, and here's my fake shellcode with Cs. And now I can pick an address in the NOP sled and write it in and take over the box same as before. That's the game. But it is a little confusing. And anyway, that's what I wanted to show you. It's a very powerful exploit. By the way, this is really easy to prevent. You just scan the source code and find the print statements that don't have a format string. But it happens. It keeps on happening. And this is why I probably mentioned already, many people are moving to Rust. C is just full of so many horrible booby traps. And there's a whole hardcore C experts, C++ people say, no, it's fine. You have to train the programmers to stop being stupid. Well, for 20 years, we tried to train programmers to use C safely, and it has failed. There are like 10 things you could do wrong in C, and they keep doing them wrong, and no matter how much you yell at them, it's too hard to remember. Oh, string isn't really a string. Oh, when you allocate memory, you have to remember to free it exactly once, never twice. And every print statement has to have a format string, and there's a few others. They always forget these things. Here's another one. If you have an integer variable, 8-bit integer, and you go up above 256, it just rolls down to 0 and doesn't tell you anything. So you add to the number and the number gets smaller. And the developer is supposed to remember this. How are they supposed to remember something like that? That's insane. So, and Rust doesn't do any of this. It's as small and as fast as C, but it doesn't do these top 10 irritating things. So I got some projects where you can see this. You can see vulnerable C code and see the Rust code. That's why a lot of people love Rust. Yeah, go ahead.
It does other annoying things instead.
Yes.
So, for example, instead of having free and memory allocation, it keeps track of the lifetimes of all the variables. And if you have a complex program where you have references to variables going here and there, now you not only have to keep track of memory management, but the lifetimes of all the variables, and define the lifetimes, and you can tell the developers of Rust did not want people doing this because the way that you do this is so obscure and so weird.
Well, yeah. Yep, that's right. So there are arguments, but in fact, both Linux and Windows are now writing parts of the kernel in Rust. They haven't released them, they're using it, but they're developing towards this. They've accepted at least the most critical code should probably be in Rust instead, because these problems have just been hitting us in the head for 20 years. Because there is best practices in C, and yet there's no way to make your developers always remember to do the best practices. It's like, it's like building a car with like sharp edges on the steering wheel. Sooner or later, you're going to get cut.
Personally, I would have rewritten the C standard library.
Microsoft did that and released it 10 years ago, and it still didn't solve the problem. They replaced like the 10 worst functions with better functions.
No, they didn't. They didn't replace it. They added them onto and then added little compiler warnings if you didn't use the new ones.
They didn't take out the,
Yes.
Oh,
I would have just said, no, you do not get those at
Yeah.
all.
Well, that's essentially what Rust does. It just has different libraries that don't have these booby traps in them. Yeah. Anyway, I'll point out that you can do Rust. I've got it in the project. You can practice doing some C and Rust and see them compare, which is a good thing to do if you're interested in development. Anyway, let me stop this video. That's all I wanted to show you before lunch.